Last time we talked about how weak acids ionize partially and how having salt or buffer solution with the same ion can affect the way they behave or with the way the solution behaves. Those are soluble, but they don't ionize fully. They remain as molecules and don't break up and make ions. What about things that are insoluble? Now, there's all sorts of reasons why something is soluble and why something is insoluble. And we talked about the enthalpy change of hydration and enthalpy change of solution whenever we were discussing group two. So let's look at them. That how exactly do they react with water, or do they even react with water? Hota kya hai? So here's the thing. Let's take a simple example of silver chloride. Now, silver chloride, if I add it to water, what I expect it to do is that it should break down into silver ion and chloride ion, and they should be aqueous. So they should move around, and that is what I would expect to happen. I want it to dissolve. And it does do that. Whenever you add silver chloride to water, it does form this. There are going to be ions that go and become aqueous, and there's going to be solid left over. At the same time, some ions are also going to come back, and we say that they will recrystallize. These ions will be on the surface of silver chloride, whatever particles you have, whatever जो भी आपने granules वगैरह add किए हैं, and they will come back to that and they will form, they will recrystallize, especially in what we call saturated solution. Saturated solution वो होता है which has dissolved the maximum amount of salt that it can dissolve at that temperature. So pretty soon you're going to see an equilibrium happen, and this equilibrium will be based on the amount of silver ions, chloride ions, and silver chloride solid. And there is going to be recrystallization, there's going to be reprecipitation, क्योंकि usually हम इसको precipitate बोल देते हैं because it doesn't dissolve and it's undissolved ionic compound in there. And this is the saturated solution of the ions that you have. And just like any other equilibrium, हम इसका लिख सकते हैं, and we can write the Kc for this, which comes out to be silver ions times chloride ions divided by silver chloride concentration. But here's the thing. It's a ridiculously insoluble salt, which means a very, very small amount of ions are going to be there. And only a very small fraction of this is going to actually dissolve, just like a very small amount of ethanoic acid actually ionized. And in that case, what we did was we said that the concentration of the solution or the undissolved or the unionized acid was very high. So we ignored that. Similarly, we have a reason to ignore silver chloride here because first of all, it's a solid, it's not dissolved. So iski concentration ki baat hi nahi banti. It's not going to be dissolved in the solution. So it's just going to be there. So we will not include this. Instead, we will just keep the ions there. And these are the ions that have actually been dissolved. And this thing, because not Kc anymore, because it doesn't follow the same idea, we just give it a different name. We call it solubility product. That this is the multiplication of the dissolved ions. So Ksp. And this is the solubility product of the equilibrium that is established of something that is dissolved, but not so much. So one important idea to remember here is that if you can dissolve more solid at that same temperature, तो अभी तो equilibrium established नहीं होया. So because of the equilibrium not being there, किसी भी unsaturated solution का Ksp नहीं होता. Ksp is only when you have an equilibrium established of a saturated solution where you cannot dissolve anymore at that particular temperature. So we just figure out the ions that are dissolved, their concentration, and we put it there. And just like that, अगर हमारे पास, for example, iron hydroxide होता, iron 2 hydroxide, and this forms this. So the solubility product of this will include this there. So हमारा Ksp should be Fe2 plus ions concentration times the hydroxide's concentration twice, because there's two of this in the mole ratio. So instead of writing this, we just say that the Ksp is OH minus squared. Okay. And another important thing, कि जब आप इसको डिसॉल्व करेंगे, so let's say we have 0.1 moles per dm cube of iron 2, so we will multiply it by 2 to figure out कि अच्छा iron इसमें हाइड्रोक्साइड की कॉन्सेंट्रेशन क्या है, and then we will square that. So उसका impact जो होता है वो 4 times हो जाता है. Obviously the unit is also based on this, so because there's 3 moles per dm cube being multiplied, our final unit is going to be mole 3 dm minus 9, and that is how we figure this out. Now every salt will have a value for any particular temperature for ksp, because just like solubility is affected by temperature and every other equilibrium is affected by temperature, the k value is also affected by temperature. And because of this, the solubility product at every temperature is fixed. Now you use that to figure out two things. एक चीज होती है that is called solubility. Solubility is basically the mass of that thing that will be dissolved in 1 dm cube at that temperature. So solubility is like the amount or mass per unit volume that is in the solution, जो maximum आप dissolve कर सकते हो. तो ये grams per dm cube में होती है for each temperature. And ksp is the constant based on that. So हम क्या करते हैं, that we use the solubility to figure out the moles that have dissolved, and we use the ice method to do that, the one that we have already seen, and then we will figure this out. So let's take iron 2 hydroxide, and again I'm just inventing these values. They actually में ये values नहीं है. So let's take the solubility of iron 2 hydroxide to be 5 into 10 power minus 10 grams per dm cube at room temperature and pressure. Pressure is not important because we are not talking about gases here, but still. Now the solubility is 5 into 10 power minus 10. मुझे इसका MR calculate करना पड़ेगा. So my MR will come out to be, so I'm just using a basic periodic table. So the MR of this is 90. Now based on that, I can see that the moles per dm cube that are actually dissolving is going to be, or solubility in mole per dm cube is going to be 5 times 10 per minus 10 divided by 90. So whatever that comes out to be. So 5 divided by 90, that is 0.0556 into 10 per minus 10. Okay, so that's my answer going to be for the concentration in terms of solubility here. So this is the concentration of iron 2 hydroxide that is actually dissolved. Okay, now let me write the equation. The equation is iron 2 hydroxide dissolves, forms iron 2 ions in aqueous solution and 2OH minus in aqueous solution. So my KSP is going to be iron 2's concentration times the OH minus concentration squared. Now, because I've dissolved all of this and this is my solubility, it's not कि अच्छा मेरे पास total mass ये था और उसमें से पता नहीं कितना dissolve होया. I don't have that. This is the actual amount of the dissolved ions and dissolved concentration of these dissolved ions. I will simply use this value. So this is going to be 0.556 times 10 power minus 10. And over here, it's going to be doubled because the concentration of this is double the concentration of iron 2 ions. So this is going to be 2 times that value, but then it's going to be squared because of that. So the effect is 4 times actually. And this is going to be my KSP. And this is telling me, Kyacha, at this temperature, this is the concentration that you're going to achieve. And this is how this is going to be. In other words, the solubility is telling me that this is the threshold. If you dissolve any mass less than this in 1 dm cube of water or 1 dm cube of solution, you will actually dissolve that thing. But if this amount is exceeded, if at that temperature you add any more mass than this amount, then you will see precipitate. So when you see a precipitate dissolve, that simply means कि उसकी या तो solubility उस temperature पे exceed कर गई है, and that is why it has dissolved, or it has formed complexes. Those are the two reasons that precipitates usually dissolve. या आप टेम्परेचर बढ़ाते हैं solubility उसकी KSP चेंज होता है जिसकी वजह से उसकी solubility चेंज होती है जिसकी वजह से वही precipitate अब dissolve हो जाता है, या फिर उसके complex बनते हैं by chemical reaction and that those complexes might be soluble. In other words, what is a soluble salt? It's just something that we see dissolve more at that temperature. And what's an insoluble salt? The one that has a lower solubility at that temperature. That's all. So every salt is soluble and every salt is insoluble in certain limits. So sodium chloride is soluble as long as you don't have a saturated solution. The moment you get saturated solution, वही sodium chloride dissolve होना बंद हो जाएगा. So at room temperature and pressure, when we say this salt is soluble, we're just saying that the solubility of that salt is very, very high at this temperature. Okay, and when it's insoluble, the solubility is very, very low at this temperature. Okay, so we can use this to figure out solubility. We can use this to figure out the concentration of that. Now, what if I have the KSP, but I don't have the solubility? Solubility is a KSP, तो हमने देख लिया कैसे करते हैं. What if I don't have the solubility and I want to figure that out? Again, really simple. Let's take silver chloride, for example. Silver chloride will make this. This is solid. These are aqueous ions. Now let's say I know that KSP of silver chloride is going to be 1.8 times 10 per minus 10 mole squared dm minus 6 because you have two ions on की concentration multiply हो जाएगी. Now I don't know how much is the concentration at this temperature. So that's fine. Let me write the KSP. KSP is going to be silver ions concentration times chloride ion concentration. Now, because I don't know how much of silver ion is dissolved and what's the concentration of that, I'll just call it X. And because the mole ratio is the same, this is also going to be X. And this will be equal to 1.8 into 10 per minus 10. So that means X squared is going to be equal to this. And if I want to figure out the concentration, not the moles, concentration of silver ion, it's going to be square root of this, which will be 1.34 times 10 per minus 10, sorry, minus 5 moles per dm cube for the concentration of silver ion. And now that I know this concentration, I know that the mole ratio is 1 to 1. So silver chloride का MR लूंगा और उसको इससे multiply कर दूंगा to figure out what is the solubility, what is the mass that dissolves in 1 dm cube of solution. Now, what if you had something in which the mole ratio was not 1 to 1? What if you had this? So in this case, you're going to get 2 of OH minus. Will it still be the same method? Yes. Let's say my KSP in this case is 0.0135. Now, what's my expression for this? Calcium ion, OH minus ion squared. Okay. But you have to understand that if this is X, then this is 2X. So that means 0.0135 is actually equal to X times 2X squared, which gives me a total of 0.0135 equal to 4X cubed. And that is something that many students struggle with sometimes. So all I need to figure this out is, gotcha, I'll take the cube root of this if I want, or I should just divide with 4 first, ताकि मेरे लिए थोड़ी सी आसानी हो जाए. Although अगर आप cube root पहले ले लो या बाद में ले लो कोई फर्क नहीं पड़ेगा. So that is going to be my concentration of this thing, if my KSP is this. But if my solubility was this, then the situation will be different. अगर यही क्वेश्चन हमें वो देता कि वो कहता कि ये KSP नहीं है, ये solubility है. So how will I solve it in that case? If solubility was 0.0135 milligrams or grams per dm cube, then all that is telling me is that this is the mass which you cannot exceed. अच्छा, let's say हमें इससे भी आगे एक स्टेप चले जाते हैं. What if हमें वो grams की बजाय moles per dm cube में ही दे दे? So that is fine. If this is telling me the solubility is mole per dm cube, that simply tells me what is the concentration of this solid that will dissolve at that temperature. So that is 0.0135. इसका मतलब है कि in this situation and in this solution, the concentration of this is 0.0135, which means the concentration of this is 0.0135. But since I have 2 OH minus, I'll multiply this by 2. So I'll get 2 times 0.0135 for this. And again, my KSP will be 0.0135 and 2 times 0.0135 squared, and that will give me my value. So whether it is solubility in grams per dm cube, you convert it to moles per dm cube. If it is given in mole per dm cube, you use that to figure out the concentration of ions and then KSP. And if it is KSP, then you use the expression, you use the mole ratio to figure out कि अच्छा वो कैसे होगा. And based on that, you can easily figure out the solubility or the other way around. And then you can predict precipitation. Because the moment you see कि अच्छा ये इसकी solubility है, that means if you exceed this value, if you have more moles in 1 dm cube than this, you will see precipitates. और उससे नीचे any salt at less than solubility values will dissolve because equilibrium तो establish नहीं होएगा, saturated solution तो बनेगा ही नहीं. Now, is there a way through which we can affect the solubility without changing the temperature? And that is called common ion effect. The common ion effect tells me that you can affect the solubility of any particular salt without changing the temperature by just disturbing the equilibrium. So let's say I have silver chloride, yay silver chloride. This will form silver ions and chloride ions. And the KSP depends on the concentration of silver ions and the concentration of chloride ions. Now imagine if I added sodium chloride, in which case the equilibrium is, compared to this, the equilibrium is so much to the right कि हम इसको बस कह देंगे कि ये dissolve ही होता है. And what do we have here? A common ion. Now the KSP is fixed at that temperature, which means it doesn't care where the chloride is coming from. वो sodium chloride से आ रहा है या वो यहाँ से आ रहा है. उस solution में KSP इतना ही रहना चाहिए, which means you have increased the concentration of this. And what happens according to the Shetland's principle? If you increase concentration of one thing, the equilibrium goes to the left. And that is what will happen. The concentration of silver ions in the solution will reduce because you have increased the concentration of Cl minus. But KSP has to remain the same. तो अगर ये बढ़ेगा तो ये कम होना पड़ेगा because this cannot change at that temperature. And this is what will create more solid. And you will see precipitates form. And this is called common ion effect. By adding something that is common, but the source is much, much more soluble than the other one, it will drive the solubility of the less soluble even more towards the left side. So पहले ही वो less soluble था, जिसका मतलब है equilibrium इस side को ज़्यादा favor कर रहा था. And then once the equilibrium was established, तो हमारे पास एक amounts fix हो गई थी. But by disturbing the equilibrium and making it go back, you have increased the precipitate that you have formed. Which gives us the idea that if I want to extract silver chloride and make more solid, all I need to do is keep on adding sodium chloride because it will keep on driving it back and I can get more and more amounts of silver chloride as precipitate. जिसका मतलब क्या होगा कि मैं उसको filter करके silver chloride बाहर निकाल सकता हूँ. And that is what we do. Now my question here might be, why can't we just have the same chloride here and here? We do. But the amount is, the amount of chloride coming from sodium chloride is much, much more than the amount of chloride coming from silver chloride. And because of that, अगर ये 0.00001 होगा और ये 0.1 होगा, तो इसमें आप इसको add कर भी दो तो कोई इतना फर्क तो नहीं पड़ने लगा. So this is negligible, the contribution of silver chloride to this. And that is why this drives it back. Okay? So this is a pretty straightforward situation कि जो चीज़ ज़्यादा soluble होगी वो कम solubility वाले को further insoluble create कर देती है because of the common ion effect. Now, let me try a question. Let's say I have KSP for calcium hydroxide, and that is 4.78 into 10 power minus 5. Now, if I had a saturated solution, then what is the concentration of calcium ion? Let's see. KSP is calcium ions concentration times hydroxide ions concentration times 2 squared. 4.78 times 10 power minus 5 is going to be x times 2x squared. So ये बन जाएगा 4x cubed equals to this. मैं इसको divide by 4 करूँगा and then I take the cube root and this will give me some value. So this value comes out to be, so x comes out to be 0.0229. That this is the mole per dm cube of calcium ion in a saturated solution. Now let's say we add uh, 0.1 mole per dm cube sodium chloride. Now sodium chloride is much, much more soluble than calcium hydroxide. It has a much higher value for uh, what you call solubility. And the temperature is still the same. So which means KSP is still the same. So what is the concentration of chloride now? The value of chloride is going to be updated because now chloride is going to be 0.1 from sodium chloride. And इससे तो कोई common effect होगा नहीं. Let's say this was sodium hydroxide. Okay, so I have added 0.1 mole per dm cube sodium hydroxide to this, which means the value of hydroxide's concentration is going to be updated. Sure, it is still 0.1 from this, but at the same time, this is also contributing to that. And the concentration of hydroxide coming from calcium hydroxide is 2 times this. तो अगर मैं उसको include करना भी चाहूँ तो I can say that this is plus 2 times 0.0229. So वो क्या आ जाती है? वो होती है 0.1 plus 2 times 0.0229 is 0.0458. So my overall value is 0.1458. You can see कि इसकी contribution बहुत ही कम है. So let's see how much of calcium ion is still going to be there. KSP is still the same. Calcium ion's concentration we don't know, but hydroxide ion's concentration we do know. Okay, and it's 2 times this squared. So KSP was 4.78 into 10 power minus 5. This has not changed because temperature is still the same. This is x. This is going to be 2 into 0.1458 squared. So that gives me 2 into 0.1458 squared. And then I'll divide that over there. The 4.78 and 10 power minus 5 divided by my answer is 0.000562 moles per dm cube. If you notice, we had this much and now we have this much. It has reduced by a factor of more than 100. Not a factor of 100 वैसे. अगर मैं इनकी रेशियो लेता हूँ तो 0.0229 divided by point, this comes out to be almost 41. That means 41 times uski solubility reduced. That's insane. That's a very, very high factor just by adding a small amount of sodium hydroxide. And that is how we can see that just having the common ion has reduced the solubility and driven the equilibrium backwards. इसका मतलब क्या हुआ? इसका मतलब ये हुआ कि अब ये है जो बच गया. पहले कितना था? पहले था 0.0229. उसमें से ये बच गया. तो कितना नहीं रहा? 0.022338 has been driven back, which means that this many moles per dm cube have become solid. So you can filter it out and get this much more calcium hydroxide from that solution. Or this is the moles per dm cube that will precipitate. And that's it for today, common ion effect, KSP. The last thing that we have is partition coefficient, but I think वो हम next class में कर लेंगे and we'll be done with this chapter. Allah Hafiz.